In this section, we'll look at a word problem involving an exponential equation, and now we'll use more sophisticated methods to solve those word problems. So in this example, a concentration of a drug in the body fluids is given by this equation. C equals C naught, so some coefficient, times e to the power negative 0.8 t. So C naught is the initial dosage. T is the time in hours elapsed after administering the first dose. So there's your independent variable. And let's just start writing this down. So I have that the concentration after T hours is equal to the initial dose. And if I look at the next sentence here, if 45 milligrams of a drug is given, there's your initial dose. So 45 in milligrams. How much time elapses until 30 milligrams of the drug remains? So I have 45 e to the negative 0.8 t. So I need to solve for how long until the concentration is equal to 30 milligrams. So I'll solve for 30 equals 45 e to the negative 0.8 t. All right, so now this is just an equation that I want to solve for t, which is time. All right, first thing I'm going to do is try to isolate the exponential, get the exponential by itself, because this 45 is kind of standing in my way there. So let me divide both sides by 45 first. So on the right, I get e to the negative 0.8 t. And on the left, 30 divided by 45 is 2/3. All right, so now what you can do to get rid of the exponential is I'll apply the inverse of log base e, which I know is called the natural logarithm. So I'll apply the natural logarithm to both sides. So now I have natural log of 2/3 equals natural log and the exponential base e undo each other. I got negative 0.8 t. And now to solve for t, all I have to do is undo this multiplication. Divide both sides by negative 0.8. So now I have my answer. T is equal to negative natural log of 2/3 divided by 0.8, which is an exact answer but isn't very useful. So I'll convert it to an approximate decimal. So I got negative natural log 2/3 divided by 0.8. So this will be approximately, and I need to round to 2 decimal places, so that'll be 0.5. The next digit's 0. The 6 rounds that up to a 1. All right, 0.51, and let's see, what type of time am I talking here? Time in hours. Hours. All right, so this problem was relatively easy because they already gave us the equation, and I had to do a little bit of work to figure out what the coefficient was, and then to plug my values in and solve for time. Let's do another example where they're not going to give me the equation. A chemist isolates 77 grams of a radioactive element and wants to calculate the half-life. He determines that after 17 days, only 36 grams of the original element remains. What is the half-life? All right, so what we have to understand here is that the amount in grams of an element left after time goes by is given by an exponential equation. A naught times some base to the power t. So now I have to figure out what all these things are. First of all, we have to declare our variables. Let's let t be time. And since I'm using, 17 days, I'll say time in days. And then A of t will represent the amount of the element in, I'm using grams to represent that, to measure that. Okay, I also like to make a chart of values. T for time, A of t for amount, So my initial amount at time 0 was 77 grams. So that's going to be my coefficient here. I might as well write that in. A of t equals 77 times a to the t. Okay, he determines that after 17 days, only 36 grams of the element remains. So let me go ahead and plug that stuff in. If I set it equal to 36, plug in 17, I should be able to solve for A. So let's divide both sides by 77. Now I got 36 over 77 equals A to the 17th. And then we can raise both sides to the power 1 over 17 to get the base. A equals 36 over 77 to the power 1 over 17. All right, let's plug that back in. I've got A of t equals 77 times the base A, which is 36 over 77 raised to the 1 over 17th power, all raised to the tth power. And this kind of looks ugly, so I'll simplify it by recognizing that when you raise a power to a power, you multiply the powers. So it'll be 77 times 36 over 77 to the power t over 17. Okay, now the question is, what is the half-life? And remember, the half-life is the amount of time that it takes for there to be half of the element left. So if I started with 77 grams, I want to know how long until 77 over 2 grams. So I guess I'm solving for t. 77 divided by 2 is 38.5. So I want to know, solve for t, set it equal to 38.5. And now I'll solve for t. Now this is an exponential equation. So in order to solve this, first I'll isolate the exponential by dividing both sides by 77. Which naturally, this should be 1/2, or 0.5. And then what I would do is, instead of using the log base 36 over 77, I would recommend applying the natural log to both sides. So natural log of 0.5 equals natural log of this whole side. And when you do that, the exponent up here comes down. And what I have left is natural log of 0.5 equals t over 17 times the natural log of 36 over 77. Okay, now again, we have to remember what we're doing. We're solving for t. So let me multiply both sides by 17 to get that out of the denominator. So I've got 17 natural log of 0.5 equals t natural log of 36 over 77. And then to get t by itself, I'll undo this multiplication by dividing both sides by natural log of 36 over 77. Okay, let's see what I have now. T is exactly equal to 17 natural log of 0.5 all over natural log of 36 over 77. And I should really get a decimal approximation for that. So 17 natural log of 0.5 over natural log of 36 over 77. So it's approximately 15 point, let's give it 4 decimal points. 4987, the next digit's 6, so that'll be 4988. Almost 15 and a half, and time was in days. Approximately. Again, so these half-life problems, they require a little bit of work. I highly recommend organizing your data in a chart, making sure that you declare your variables so we know what we're dealing with. Time is in days and amount is in grams. And then it's kind of easy to know what to plug in if you know what your variables represent.